Welcome to this introduction to programming in Lean. In this small tutorial, we will discuss types and terms in Lean, functions, definitions. We will understand how to evaluate functions in Lean, and finally we will take a tiny glimpse at pattern matching, which is a way to define functions. The contents of this tutorial are a subset of Chapter 2 of the online textbook Theorem Proving in Lean. This link down here is a direct link to Chapter 2, which I encourage you to read after having watched this tutorial. We start out by looking at types and terms in Lean. We've already encountered some types and terms in Lean. In particular, we have seen types as the domain of reasoning in predicate logic. So we have used often an arbitrary, like a general type U, to discuss predicates on U in predicate logic. We have also sometimes studied particular predicates on the domain of natural numbers. And now we are going to look a bit more in detail at what kind of operations we have available on natural numbers. First of all, we can ask Lean, what is the type of the natural numbers? So as before, this bold font N denotes the type of natural numbers in Lean. We can ask Lean, what is the type of the natural numbers? And it will tell us, well, the natural numbers are a type. Next, we can ask, what are the elements of the natural numbers? And we know from the mathematics class of the first term that we have in the natural numbers with an element called 0. And we can ask Lean, what is the type of 0? And Lean will tell us that 0, which it writes here as a number, not spelled out, 0 has type natural numbers. So for Lean, this 0 is entirely synonymous with the 0 spelled as a number, 0, for which it gives us the same answer here. We have more natural numbers. We can ask Lean, what is the type of 3? And 3, Lean will tell us, is also a natural number. So more generally, what is a way to build a new natural number from an old one? That way is the successor function. The successor is a function from natural numbers to natural numbers. So it takes as input a natural number, and it gives us an output, another natural number. The successor function is the first example of a function on the natural numbers on a domain of reasoning and predicate logic that we're seeing. We can ask Lean, what is the successor of 3? What is the type of the successor of 3? Well, that's again a natural number. So 3 is an input to the successor function, and the output is again a natural number. We have more operations on the natural numbers. For instance, we have the operation plus, and we can ask Lean, what is the type of 3 plus 5? And Lean will tell us that the type is the natural numbers. We also have an operation minus, and when we ask Lean what the type is of 1 minus 5, Lean will tell us that that is a natural number. We will later see how to ask Lean to evaluate what 1 minus 5 is, but not yet. Besides these constants of natural numbers, we can also declare variables. For instance, here we declare a variable x of natural number type, and then we can use x like any other natural number. For instance, we can ask what the type is of x plus 4, and Lean will tell us that this is again a natural number. The natural numbers are just one among many types in Lean. We also have, for instance, the type of booleans. So the booleans are another type. And the Booleans have only two canonical inhabitants. Firstly, TT, which is a term of type bool, and secondly, FF, which is also a term of type bool. We can think of TT as meaning true and FF as meaning false. In addition to these constants of type Boolean, we also have operations on Booleans. For instance, we have the double ampersand operation, which is a logical or a Boolean AND operation. And when we ask Lean what the type is of true and false, it will tell us that this is again a Boolean. As before, we can declare variables. This type of variable b of type bool, and we can use this variable as if it were a constant. For instance, we can AND it with another term of type Boolean, here FF, and Lean will tell us that b and FF is a term of type bool. The third example of types that we are looking at in this tutorial is the type of lists. For instance, here the type of lists of natural numbers. So list n is a type in Lean. And here we have an example of a term of that type. This is a list containing natural numbers as elements. So the term 3870 is a list of natural numbers. So list n is a type whose elements are lists, whose inhabitants or whose components are natural numbers. We have also the empty list, which is just written like this, just brackets open and closed. For Lean, this is synonymous with list.nil. So nil is another word for the empty list. And Lean shows us here that this list is actually a list over any type. So here Lean has trouble figuring out what it should write here. So it writes just question mark m, which could be any type. Since this list doesn't have any entries, Lean doesn't know what the type of entries of this list should be. We can, however, indicate what it should be. So let's write something here. We can ask Lean, what is the type of the empty list seen as an empty list of natural numbers? And then Lean will tell us that the empty list seen as a list of natural numbers is indeed a valid term, and it has the type that we are imposing it to have. Without such a type annotation, Lean will not know what entries we are considering for the empty list. Okay, so list itself is an interesting construction because it is itself a function. It takes a type as an argument and it returns another type. So if we look at the type of list, we see that it's a function that takes a type as an input and returns another type as an output. This means in particular that we can apply list several times. So we can consider the type of lists over natural numbers and then apply the list function again to this type. And this gives the type of lists of natural numbers. Here I have written a term of that type. So this is a list whose individual entries are themselves lists again. Here, for instance, the first entry is a list of length 2. The second entry is the empty list or is an empty list. And the third entry is another list of length 3. And Lean tells us that this list, this term, is of type list of n. So as before we have seen that the empty list is a term of any list type. In particular, we have the empty list seen as a list of lists of natural numbers. So Lean happily accepts that the empty list is a term of type list of n. After looking at these types, we will focus on one particular type construction, which is the type of functions in Lean. A function in Lean is written using the keyword lambda. Lambda marks the input of a function. The general syntax for a function in Lean is as follows. We write lambda a in a, comma, and then the definition of the function that we are interested in. We will see some examples. First, I want to let you know that lambda is actually synonymous with the keyword assume that we have already encountered in the context of logic. Lambda can be seen as the programming equivalent to this logical assume keyword. So let's look at our first example of a function in Lean. Here we define a function. Let's look first at the type. We define a function goes from natural numbers to natural numbers. So it takes an input, as input a term of natural number type, and it gives as output another term of type natural numbers. And this function is defined as follows. It takes an input that we call n, and n has type natural number, and as output it gives us the successor of n. So this function, I repeat, it takes an input that is of type natural number, and we call this input n, and in the definition of the function we can mention this n and tell us and declare to Lean what we do to this n to compute the output. So here we apply successor to the input n. As I've said, the keyword assume is completely synonymous with the keyword lambda. So here we declare the same function, assume n, successor of n, and when we ask Lean what the type of this term is, it actually does replace assume automatically with lambda for us, and it tells us that the type of this term is again nRON, a function from the natural numbers to the natural numbers. It is important to note that the name that we give to the input here is our choice, as long as we are consistent. When we can pick any name here for the input. Instead of the input name n that I chose here for this first term, here I choose the input name x, and I replace n here with x everywhere, and I obtain the same function. So lambda x, successor of x, is exactly the same as lambda n, successor of n. So to summarize, all these three terms that we have looked at here are exactly the same for the purpose of Lean. Here we define another function that is a function on the booleans. It takes as input a boolean and it returns the boolean that is b, which is the input, and true. So this is again a function that takes one input of type bool, and it returns an output of type bool. We can write another function which now takes two inputs, an input b1 of type bool and an input b2 of type bool, and it returns b1 and b2. b1 and b2 is again a boolean, so the output of this function is a boolean, but this time we have two inputs. This input corresponds to b1 and this input here corresponds to b2. Interestingly, Lean applies a sort of a tiny simplification here. We have written lambda b1 of type bool, lambda b2 of type bool, and Lean just collapses these two lambdas and writes this shorter as lambda b1 b2 of type bool. So this is completely synonymous. We can contract two lambdas into one lambda here to have a more compact way of writing functions. The type annotation at the variable of the input of a function can be omitted. Here we write lambda n successor of n, and we omit the type annotation of n here, of the input of the function. The type of n can be deduced from by Lean from how n is used in the body of the function, in the definition of the function. So when we give this input to Lean, Lean understands that here n should be a natural number, and it will automatically annotate the variable with its type for us. I generally would recommend against omitting the type annotations. It's bad style and your code will not be very readable, in particular when the code becomes more complicated. So this is a way to write functions. Now we want to apply functions to arguments, and function application, this is simply written by juxtaposition. So here we have a function, the function that we have seen before, that maps a natural number to its successor, and we apply it to an argument, here to the argument 5, simply by juxtapositioning the function with its argument. And when we apply a function to its argument, then the type is that we obtain is the output type of the function. So here the type of this term is the type of natural numbers, because this function is a function into the natural numbers. Here we see another example of a function application. We have a function from booleans to booleans, and we apply it to a boolean, and then the output is another boolean. Let me write another example here. Assume we have a function is 0 from nut to bool. Then we can check what is the type of is 0 of 3. So here we apply the argument 3 to the function is 0, and Lean tells us that this term, which is the function application, is of type bool. So when we apply a function to a suitable input, then we obtain a term that it has the output type of the function. Okay, the next tiny section in this tutorial is about definitions. A definition is a way to store a complicated Lean expression or a complicated Lean term or type in a short notation in some sense. Here, for instance, we define a term foo, which is a term of natural number type. And we define foo to be the natural number 5. So the format of a definition is we start with the keyword def for definition, and then we can choose a name of our liking, and we'll annotate it with the type that we want this term to have. Here, natural numbers. This is done with the colon, as always. And once we have specified the type of the constant that we're defining, we can give its body, its definition. And this is done by writing colon equals, followed by the actual definition. When we check the type of foo, we see that foo is a constant of type natural numbers. We can now print foo, and the print command will tell us what the definition of foo actually is, and it will tell us that foo is defined to be 5. So now, whenever we use foo, it will actually mean 5. We can do the same thing, omitting the type annotation. So here we define bar to be 6. This is, again, is considered to be bad style. I wouldn't do it, it results in very unreadable code. But Lean will happily accept bad quality code in this case. So here when we check bar, it will tell us that bar is of type natural number, which it has deduced just from the type of 6. So when we print bar, we see that Lean has inserted for us the type annotation. Definitions cannot just be constants, like constant terms, like we have seen for foo and bar, but definitions can also have parameters. And these parameters are mentioned right after the identifier that we can choose ourselves. Here we define a term successor, which takes one parameter, and the output of this, so the type of successor is natural numbers. And the definition of successor, in the definition we can now use the parameter that we have declared here, and we can say the successor of the input n is n plus 1. So now we have defined successor, a Lean term. It has type natural numbers to natural numbers. This n here stands for the parameter n of the definition, and the output here stands for the n plus 1, which is the definition of successor. So this definition here is actually completely equivalent to writing definition successor prime of type natural numbers to natural numbers, and we declare this to be lambda n n plus 1. These two definitions, this one and this one, they are completely synonymous. If we print the successor constant that we have defined here, we will see that Lean actually rewrites our definition, where we have used a parameter up here, into the second definition that I've given in terms of lambda. So this lambda n colon n here is completely synonymous to giving such a parameter to a definition. Let's write some more complicated functions. Here I define a function called foobar, which takes as input two natural numbers, x and y, and a list of natural numbers called s. And it returns then another list of natural numbers, which is the list x, y, and then the list s appended to this initial list. So the type of this constant that we have defined is n arrow n for the two inputs x and y, arrow list for the input s, and then arrow list n for the output, which is this list here. I've written this in a very bad style. I've omitted the output type. Here I have written the same function in a better style, where I have added the output of foobar, which I call here foobar2, because I cannot use the same name twice. So here I indicate the output of the function, which is this list here, which is a list of natural numbers. Again, these parameters, they can equivalently be declared using lambda notation. So synonymously with this definition, we get this definition here, where we declare foobar3 to have the following type: n arrow list n arrow list n, and we declare it to be the lambda term, the term starting with a lambda, taking as inputs x and y, two natural numbers corresponding to these two arguments here, then a list of natural numbers corresponding to this list n here, and then the output. So after this comma here, we have the output of the function, which is a list of natural numbers, and this corresponds to this part of the type here. In the last, or second to last part of this video, we will look at how to evaluate functions in Lean. We can explicitly ask Lean to compute the result of a function application to an argument. This is done with the command reduce, which is always preceded by a hash. We've seen before the successor function, lambda n successor of n, and let me add a type annotation here, so I should follow my own advice. Lambda n successor of n is a function taking a natural number as an argument and returning its successor. And when we apply this function to an argument, here 5, then Lean can compute the result for us. It will tell us that the successor of 5 is 6. In the second example of computation here, we have a function that takes an input, again a natural number, which we call x here, and it outputs x plus 3, which is again a natural number. If we apply this function to an argument, here 5, Lean can tell us what the result of that application is. It will tell us that the result is 8, which is 5 plus 3. We can also compute with booleans. Here we have a function that computes for an input b. It computes b and f. If we apply this function to the input true, the function will spit out f, just because really any boolean, if it's AND it with false, will return false. Here's another example of a function application. We have a predefined function that is called mod, and so it computes the remainder of a division. If we divide 7 by 3, we get remainder 1. And here, so Lean can tell us can evaluate this function for us. It tells us that mod 7 mod 3 is 1. So the type of this NUT mod operation, we don't actually need the prefix NUT because we have opened the corresponding namespace. So let me take this away. Maybe we do need it. If we check this function, NUT.mod, Lean will tell us that it's a function that takes two arguments, two natural numbers as arguments, and it returns another natural number, which is the remainder of the division of the first by the second. After these examples of function evaluation, we will discuss very briefly pattern matching, which is a way to define functions on various data types. For instance, here I define a function bitflip, which takes a boolean as input and returns a boolean as output. And pattern matching is a way to define such functions by specifying what to do on every kind of input. For instance, the function bitflip, on the input true, it should return false, and on the input false, it should return true. And this is indicated by the following syntax. We have a case distinction depending on what the input is, and every case is indicated by a pipe, by this symbol here. So here pipe TT means this is what this function should do in the case that the input here, is TT. And then we have a colon equals, and then we have what we want to, we specify what we want the output in this case to be. So for the input TT, we specified the output FF. For the input FF, we specify the output TT. We can now evaluate this function bitflip. If we evaluate it on TT, it evaluates to FF. This is exactly what we told the function to be. If we evaluate it on TT, it should output FF. Conversely, if we evaluate it on FF, we end up in the second case of this case distinction. And in this case, the function returns tt. And indeed, if we ask lean, it returns tt. Plus is another function that we can define by pattern matching. So plus is a function that takes two arguments, two natural numbers as inputs, and returns a natural number as output. Here we define plus by pattern matching on two arguments. We pattern match on the first argument 0 and on the second argument n. In the case that the two inputs are 0 and some natural number n, we want the output to be n. In the case that the inputs are of the form successor of some natural number m and n, we output the successor of plus m and n. This results in a function that we can evaluate on various inputs. For instance, if we compute the sum of plus 3983 and 123, we obtain the result 4106. This was our tiny introduction to functional programming in Lean. You can see much more of many more examples and many more features of Lean if you go to this chapter in the book Theorem Proving in Lean, where you will see many more features and more tricks on how to actually do actual programming in Lean. See you soon again.